For 40 million years, it was a ghost, a 1,000-kilometer scar across the Earth, stretching from the Yukon into Alaska, dismissed by geology as a dead and silent thing, a relic, an ancient fracture that had not moved, had not ruptured, had not mattered in the entire span of human history and far beyond. They called it the Tintina Fault, and they were wrong. Right now, beneath the quiet boreal forests of northwestern Canada, a debt is coming due. High-resolution satellite data, published in August 2025, revealed something that decades of fieldwork had missed. The Tintina Fault is not dead. It is accumulating strain. The ground on either side of this massive geologic seam is moving, building a slip deficit that has now reached 6 meters. That is 20 feet of stored energy, waiting for a trigger, enough to produce a magnitude 7.5 earthquake, not in a remote, empty corner of the world, but directly beside a community of 1,600 people who built their lives on ground they were told was stable. The town is Dawson City, and it is facing a threat it was never designed to withstand. Let us know in the comments what you think a town of 1,600 people can even do when a monster like this wakes up beneath them. An incredible number of you watch these documentaries, getting to the core of these complex stories. But the data shows most of you forget to subscribe. If this is the kind of storytelling you value, the deep dives that go beyond the headlines, then take just 1 second and hit that button. It is the single most important action you can take to make sure we can keep making them. Now, the story of how they found this threat begins in the forest. The old maps were drawn by geologists, walking the ground, hacking through dense undergrowth, trying to read a landscape that was actively hiding its secrets. The dense spruce and birch of the Yukon wilderness formed a nearly impenetrable blanket over the Earth's surface. It hid the evidence, the ancient ruptures, the massive ground shifts, the scars from quakes that had torn the territory apart millennia ago. They were all there, waiting, but invisible to the human eye. Then came the lasers. Theron Finley, a young surficial geologist with the Yukon Geological Survey, was part of a new generation of scientists armed with a technology that could see through the trees. Literally. Using drone-mounted LiDAR systems, they flew transects over the fault line, firing millions of laser pulses toward the ground. Most pulses were reflected by the canopy, the leaves and branches, but a fraction of them punched through, hitting the true ground surface below and bouncing back to the drone's sensor. The result was a point cloud, a digital ghost of the landscape. With the trees computationally stripped away, a new picture of the Yukon emerged. One that was not serene. It was violent. The data revealed massive, unmistakable scarps. Cliffs formed where the ground had snapped and vertically shifted during ancient earthquakes. They saw offset river channels, streams that once flowed straight but were now bent at sharp angles where the fault had dragged one side of the landscape past the other. The ground had moved by hundreds of meters, sometimes a full kilometer. The evidence was undeniable. The Tintina Fault was not just active, it was a beast. Finley and his team at the University of Victoria published their findings in August 2025 in the journal Geophysical Research Letters. The paper was a bombshell, dropped into the quiet world of Canadian seismology. It stated that the fault, believed dormant for 40 million years, had in fact produced multiple large, surface-rupturing earthquakes within the last 2.6 million years. The most recent major event was roughly 12,000 years ago. For geologists, 12,000 years is the blink of an eye. And since that last rupture, the tectonic plates have not stopped moving. The strain has been building in silence. 6 meters of it. Imagine 2 tectonic plates grinding past each other, stuck. For centuries, for millennia, they refuse to budge, and the elastic energy builds, year after year. That stored energy is the slip deficit, and when it finally releases, it does so all at once. 6 meters of movement in a matter of seconds. What does that look like? Less than 20 kilometers from this loaded fault line sits Dawson City, a town built on permafrost and river sediment, a place where many historic buildings stand on wooden foundations set down a century ago. A magnitude 7.5 earthquake would not just be a tremor, it would be a liquidation event. The very ground beneath the city could turn to fluid. The shaking would be catastrophic. And the secondary effects could be even worse. Looming over Dawson are 2 enormous, unstable masses of earth. The Moosehide landslide and, directly across the Yukon River, the Sunnydale landslide. These are not small slips of mud. They are entire hillsides, saturated with ice and rock, barely holding together. Scientists have warned for years that a strong seismic shock is the one trigger that could send them collapsing into the valley, across the river, and potentially into the town itself. The 2025 paper by Theron Finley's team was not a historical finding, it was a forecast, a warning that the seismic hazard model for the entire region was fundamentally wrong. The biggest threat to the Yukon was not a distant possibility, it was a mathematical certainty, coiled and waiting just beneath the surface. And then, 4 months later, the ground started to shake. On December 6, 2025, at 11:41 a.m. Alaska time, it happened. A massive MW 7.0 earthquake ripped through the remote wilderness near the Yukon-Alaska border. The epicenter was shallow, only 10 kilometers deep, meaning the energy released was not muffled by miles of crust. It slammed directly into the surface. The shaking was violent, radiating for more than 50 miles across a landscape of rock and ice. Thankfully, the rupture occurred beneath the Hubbard Glacier, a vast and unpopulated ice field. There were no buildings to collapse, no highways to buckle, no towns to flatten. The closest Canadian community was Haines Junction, Yukon, roughly 130 kilometers away. Residents there reported a strong, rolling motion. Books fell off shelves. Pictures rattled on walls. Alison Bird, an earthquake seismologist for Natural Resources Canada, became the public face of the event, relaying information to a nervous region. "Mostly people have reported things falling off shelves and walls," she told reporters. "It doesn't seem like we've seen anything in terms of structural damage." The damage was minimal. The message was not. This was not a random tremor. Seismologists quickly identified its source. A previously obscure fault, now dubbed the Connector Fault, which acts as a physical link between two much larger and more dangerous systems, the Tintina Fault and the Fairweather Fault. For geoscientists, this was a terrifying confirmation. The tectonic plumbing of the region was not just active, it was interconnected in ways that amplified the total risk. An earthquake on one fault could now transfer stress to another, potentially triggering a cascade. The December 6th quake was the warning shot. It was the system announcing its presence. And it wasn't done. A vigorous sequence of aftershocks rattled the border region right through the holidays. On New Year's Eve, as the world celebrated, a swarm of quakes between magnitude 5.0 and 5.7 struck the same area. The ground refused to settle down. If you've ever felt an earthquake, even a small one, describe that feeling in the comments. That sudden realization that the ground we stand on isn't solid, that it can move. The ongoing aftershock sequences in 2026 kept researchers at Natural Resources Canada on high alert. This wasn't just a single event, it was a process, a large-scale readjustment of the crust. The December quake had proven that the calm in Canada's north was an illusion. The region was a complex, interlocking machine of seismic threats, and one of its most important gears had just turned. And while the land itself was revealing its dangers, an even larger, more consequential discovery was being made just off the coast. An entirely different kind of threat, one that doesn't just shake the ground, but moves the ocean. For decades, the biggest earthquake threat to Canada's west coast was thought to be singular, the Cascadia subduction zone, a monster fault running from Northern California to Vancouver Island, capable of producing a magnitude 9.0 megathrust earthquake and a catastrophic tsunami. All the planning, all the funding, all the public fear was focused south. But the north had its own monster. On August 22, 1949, a magnitude 8.1 earthquake ruptured along the Queen Charlotte Fault, offshore of the Haida Gwaii archipelago in northern British Columbia. To this day, it remains the largest earthquake ever recorded in Canadian history. It was a strike-slip event, meaning the Pacific Plate and the North American Plate slid horizontally past each other. The shaking was immense, but because the motion was mostly sideways, it displaced very little water. There was no major tsunami. Then, on October 27, 2012, another large quake, magnitude 7.8, struck the same region. But this one was different. It behaved strangely. The seismic data showed an unusual amount of vertical thrust motion, something not typically expected from a strike-slip fault. It generated a tsunami, small but measurable, that sent alerts across the Pacific. Geologists were puzzled. It was as if the fault was trying to do something new, as if it was changing its fundamental nature. That suspicion lingered for a decade, a nagging question in the back of scientific papers and conference presentations. Then, in the summer of 2025, a research vessel, the Marcus G. Langseth, sailed into those waters with a new tool, a 15-kilometer-long underwater hydrophone array, a streamer of acoustic sensors 9 miles long, towed behind the ship, listening to the deep structure of the Earth. The science team, led by Colin Brandel from Columbia's Lamont Doherty Earth Observatory and including Professor Mladen Nedimovich from Dalhousie University, was trying to create the first-ever high-resolution 3D map of the Queen Charlotte Fault system. They used an array of air guns to send sound waves deep into the crust. The hydrophones listened for the echoes, measuring how the sound bounced off different rock layers miles below the seafloor. What they found, published in the journal Science Advances in July 2025, changed our understanding of the entire Pacific coast. The Queen Charlotte Fault was not just a strike-slip boundary anymore. The data was unequivocal. In this region, the Pacific Plate was no longer just sliding past North America. It had begun to dive beneath it. The fault was actively transitioning into a subduction zone. Right now, in geological real-time, geoscientists are watching the birth of a megathrust fault. This region is actively becoming a subduction zone, Colin Brandel stated. Our study provides the first direct observations of the Haida Gwaii thrust, the megathrust of this system. They had found the infant version of Cascadia, a place where two tectonic plates are locking together, building stress that will one day release in a massive megathrust earthquake, the most powerful type of earthquake on the planet. And because one plate is being forced under another, the inevitable result of that rupture will be a massive, sudden displacement of the seafloor, a tsunami, one that would be generated just off the coast of northern BC, giving coastal communities and the entire Pacific Basin almost no warning time. This isn't just a bigger earthquake risk. It's a different kind. The 1949 quake was Canada's largest, but it was a horizontal slip. This new, developing fault is a vertical thrust, the kind that lifts the entire ocean. The misconception that Cascadia is the only tsunami source for the West Coast was shattered. A new threat, arguably more immediate for the northern coast, had just been confirmed. A subduction zone in its infancy, with all the destructive potential that implies. If you're getting value from this analysis, please take a moment to hit the like button. And if you have family or friends who need to understand the real science behind these headlines, not just the scare stories, share this with them. It helps get this crucial information out there. And I know this is the second time I'm saying this, but it really is important. If you're not subscribed yet, please do it now. A huge number of you watch these videos, but our subscriber numbers don't reflect that. And your subscription is the key signal that allows us to keep going this deep. It helps more than you know. So now there are three distinct, massive threats coming into focus. A newly awakened 1,000-kilometer fault under the Yukon, loaded with 6 meters of strain. A proven connector fault system on the Alaska border that is actively popping off with magnitude 7.0 quakes. And the birth of a brand new megathrust subduction zone off the coast of Haida Gwaii. Any one of these would be a generational concern for geologists. All three appearing at once signals a fundamental re-evaluation of Canada's seismic stability. But there is another factor at play here, a force multiplier that links all of these terrestrial threats to a global crisis. Climate change. The warming of the planet is not just melting glaciers and raising sea levels. In the north, it is actively making the ground itself more dangerous. Two interconnected processes are at work. The first is called glacial isostatic adjustment, or GIA. During the last ice age, northern Canada was buried under an ice sheet miles thick. The sheer weight of that ice pressed the Earth's crust down into the mantle, like a thumb pressed into a rubber ball. For the last 10,000 years, as that ice has melted, the crust has been slowly rebounding, rising back up. This process of crustal unloading is not gentle. As the land rises, it cracks and shifts, triggering what are known as normal faulting earthquakes. These are common across northern and eastern Canada, often appearing as small, sporadic seismic swarms in places far from any major plate boundary, like Quebec or Nunavut. GIA adds a baseline level of seismic stress to the entire northern continent, a constant readjustment that can help nudge other, larger faults closer to their breaking point. The second, and more alarming process, is the thawing of permafrost. Much of the Yukon, including the area around Dawson City and the Tintina Fault, is built on ground that has been frozen solid for thousands of years. This permafrost acts like a cement, binding soil, rock, and ice into a stable, rigid mass. But as the climate warms, that cement is melting. In March 2026, a research scientist with Natural Resources Canada, named Jeremy Gosselin, published a crucial study on this exact problem. His team had been analyzing soil stiffness at 14 different sites across the southwestern Yukon, the very region shaken by the December 2025 quake. They were building a new model to understand how the ground itself would behave during an earthquake. What they found was a terrifying feedback loop. Frozen permafrost is stiff and rigid. When seismic waves from an earthquake pass through it, they travel quickly and with relatively low amplitude. The ground shakes, but it is a hard, fast jolt. But when that same permafrost thaws, it transforms into a soft, water-saturated slurry of mud and sediment. Soft ground does the opposite of hard ground. It slows seismic waves down and dramatically amplifies their amplitude. The ground doesn't just jolt, it rolls and liquefies. The shaking becomes far more violent and lasts much longer. The implications are profound. A magnitude 7.5 earthquake on the Tintina Fault would be catastrophic under any circumstances. But the same earthquake in a future where the surrounding permafrost has thawed will be exponentially more destructive. The warming climate is literally turning the ground into an amplifier for seismic energy. Every degree of warming makes the shaking worse. This creates a chilling convergence. The geologists are finding the loaded faults. The seismographs are recording the warning shots. And the climate scientists are documenting the one change that will make the inevitable impact of those quakes even more devastating. It is a perfect storm of geological discovery and environmental change. And it all leads back to a fundamental question of preparedness. The science has moved at light speed. The discovery of the Tintina's activity, the confirmation of the connector fault, the birth of the Haida Gwaii megathrust, all have came within a single 12-month period in 2025. But has our policy, our engineering, and our building codes kept up? The answer is no, not even close. Natural Resources Canada maintains the National Seismic Hazard Model. It's the Bible that informs the National Building Code of Canada. This model determines how strong a bridge needs to be, how deep the foundations of a hospital must go, how much reinforcement a school requires to withstand a given level of shaking. It is the basis for all engineered safety in the country. The sixth generation of this model, integrated into the 2020 and 2025 building codes, was a massive update, incorporating decades of new science. But the Tintina Fault isn't in it, not as an active threat. Because its true nature was only revealed in August 2025, the models that engineers are currently using to design infrastructure in the Yukon do not account for a magnitude 7.5 rupture just kilometers away. The roads, mines, pipelines, and buildings across the territory are being built to a standard that is now known to be dangerously obsolete. This is the gap that keeps scientists like Theron Finlay awake at night. Over the past couple of decades, there have been a few small earthquakes of magnitude 3 to 4 detected along the Tintina Fault, but nothing to suggest it is capable of large ruptures, he explained, recounting the old thinking. The expanding availability of high-resolution data prompted us to re-examine the fault, looking for evidence of prehistoric earthquakes in the landscape. They found it. But now the discovery has to make the leap from a paper in a scientific journal to a line in an engineering code. That process can take years. Years that Dawson City might not have. Local researchers are lobbying hard to get the model updated, to force a change in how the Yukon prepares for its own future. But they are fighting against inertia, budgets, and the slow-turning wheels of bureaucracy. They are in a race between discovery and disaster. Every new building constructed under the old code is another potential failure point. Every unprepared piece of infrastructure is a liability. The science has delivered the warning. The question is whether anyone is listening and how fast they can act. The ground beneath northern Canada isn't waiting for the committee to approve the minutes. The situation mirrors the challenge on the coast. The discovery that the Queen Charlotte Fault is a nascent subduction zone fundamentally changes the tsunami risk profile for northern BC, Alaska, and even the wider Pacific. Old evacuation plans, based on a Cascadia scenario far to the south, may be inadequate. The warning time from a Haida Gwaii rupture would be measured in minutes, not hours. The wave height models need to be completely redrawn. The work done by Colin Brandel and his team wasn't just an academic exercise. It was a direct challenge to every emergency planner on the coast. It is a story of two different Canadas. For decades, seismic risk was seen as a southern problem, a Vancouver problem, a Cascadia problem. The north was vast, empty, and geologically quiet. That story is now being aggressively rewritten. New technology, from drone-based lasers to deep-sea hydrophones, has peeled back the curtain, and behind it lies a region far more dynamic and dangerous than we ever imagined. The pieces are all on the board. The loaded strike-slip fault, with a 6-meter det aimed at a historic town. The unstable landslides hanging above it. The interconnected fault systems waking up with powerful remote quakes. The new megathrust being born in the ocean. And all of it, supercharged by a warming climate that makes the ground itself less stable. All right, I know. Third time's the charm. But if you made it this far into the geological weeds and still haven't subscribed, we're basically best friends now, so let's make it official. It genuinely makes all the difference. The story of northern Canada's seismic risk is not one of a single threat, but of a cascading system. It shows how interconnected our world is, how melting ice can change the way an earthquake feels, how a discovery on a single fault can reframe the risk for an entire continent. We are watching a geological paradigm shift in real time. Canada's north is not sleeping. It is waking up, and it is sending tremors south, not just through the ground, but through the very foundations of our scientific and engineering assumptions. The risk is no longer theoretical. The December 2025 earthquake was a 7.0 magnitude announcement that the rules have changed. The science has provided the map of these new dangers. The data is clear, inescapable. The old view of a quiet, stable north is gone, replaced by a complex tapestry of active faults and multiplying risks. We now know where the dangers lie. The Tintina, the connector, the nascent Haida Gwaii megathrust. The real question is no longer what is happening beneath the ground. The question is what we are going to do about it on the surface.